coordinate system, okay. Actually, the title is curvilinear coordinate system, okay. The reference textbook is Weber. There he has given a lot of logic behind each and every mathematical step and each and every definition. But here, let me try to make it quite comfortable, okay, for our what you call syllabus. Not all mathematical derivation will be taken here, but better to read Weber, okay. In Weber, I think it's chapter 3, vector analysis. In that one, there is a topic like curvilinear coordinate, okay. Just note on that one. Or I think in the this appendix part of Griffiths also, there is a curvilinear coordinate system, okay. I mean, but this what you call these notations may be quite different, okay, from Weber to what you call Griffiths and all. So be careful in that one, okay. So let me take a generalized curvilinear coordinate system, orthogonal coordinate, okay. Again, we always deal with orthogonal coordinate system, okay, in most part of the physics, okay. We always deal with orthogonal coordinate system. Again, in that orthogonal coordinate system, let me take the heading, orthogonal curvilinear coordinate, okay. I mean, in the most general, okay. Coordinates. Okay, let me take generalized situation, okay. Generalized situation, okay. Now let me define coordinates as suppose Q1, Q2 and Q3. Is that okay? Again, it's just like X, Y, Z. It's just like R, theta, phi in case of our spherical polar coordinate. It's what you call your rho, phi, Z, okay. We don't write rho, we write S actually, because rho is used for charge density, isn't it, in case of electrodynamics. To avoid the confusion, we use a S here in case of cylindrical coordinate, isn't it? Whatever I'm writing, these are the, again, Q1, Q2, Q3. So they are one of these, okay? That's what I'm addressing. So now, again, these are the coordinates. We can write unit vectors, am I right? Unit vectors, E1 cap, E2 cap, and E3 cap, okay? I call it as a unit vector. Corresponds to, again, respective coordinate system, okay? Let me write like this, E3 cap. Just like here, X cap, Y cap, Z cap, okay? X cap, Y cap, Z cap. R cap, theta cap, phi cap. S cap, phi cap, Z cap. Is that okay? I mean, let me what you call work out some generalized equations, okay? So that later, what you call, I mean, you don't have to by heart some formula. You can remember some relations and you can execute that one for spherical and what you call cylindrical. We already remembered curl, divergence, gradient. I mean, the surface area, volume integral, everything for Cartesian coordinate, isn't it? Now we need to deal those things. I mean, those derivatives and integral in other two coordinate system. Okay, that's the basic idea here. Now these are the coordinates. These are the unit vector. This unit vector in case of orthogonal coordinate system, okay, it should follow this one. E1 cap cross E2 cap, that's equal to E3 cap. E2 cap cross E3 cap should be equal to E1 cap. E3 cap cross E1 cap is equal to 3-1 E2 cap. It should be cyclic in order, just like again we have taken, am I right? X cap cross Y cap, Z cap. Y cap cross Z cap, X cap, am I right? So again, they are orthogonal to each other. You can see this expression itself, am I right? They are orthogonal to each other, they are unit vectors again. Their magnitude equal to 1, okay? So in case of orthogonal curvilinear coordinate system, look at here, again, one more thing, EI dot EJ is equal to, I think, can I write delta IJ? Speak out. If I equal to J, I mean, they have a unit length. If I not equal to J, again, they are orthogonal to each other, okay? In case of any orthogonal coordinate system, you can write this expression. Is that okay? E1 dot E1, am I right? That is mod E1 square, that's equal to 1. But E1 dot E2, that's equal to 0, isn't it? Speak out. So like that. Again, these relations are related to this orthogonal curvilinear, I mean this orthogonality part, okay? So this you can see here. Now, suppose if I take origin here, okay, I'll not take X, Y, Z or something because I'm not talking about what kind of coordinate system that I'm using, okay? So again, I will write a representative things here. So I have a what you call radial vector, okay? I have a radial vector which is characterized, again, I have a position vector of a point in space which is characterized by q1, q2, q3. Just like x, y, z, r, theta, phi, rho, phi, z, like that. Is that okay? So now one thing should be clear. This r is a function of q1, q2, q3, isn't it? Your position vector from the origin, okay, is a what you call function of q1, q2, q3. So can I write like this? Speak out. Now once you write like this, you can write dr. Again, so calculus gives us this one, dou r by, okay, dou q1 dq1 plus dou r by dou q2 dq2 plus dou r by dou q3 dq3. So can I write like this? Speak out. That okay?
Yes, sir.
Now look at here. I think I will take it as a definition, whatever I'm going to write now, okay? Just see Weber for more logic, okay? This is dou r by dou q1, okay? It is along E1 cap. It is along E1 cap. Unit vector corresponds to this coordinate system. I mean, so corresponds to this coordinate actually. Is that okay? And the proportionality factor, we write it as H1. Is that okay? Again, it has some name, okay? The metric element or something. Actually, in tensor analysis, those kind of words are what you call more relevant, okay? But here again, to remember some formula, this H1, H2, H3, that's what I'm going to define. Those are very important. Is that okay? Now look at it. H1. What is H1? H1 is nothing but modulus of this vector. Is that okay? If you put mod, E1 cap mod is what you call 1. This is H1 is nothing but mod of this one. Is that okay? So similarly, I'm going to write, look at here, dou r by dou q2 derivative, partial derivative with respect to second coordinate, partial derivative of our what you call our position vector, am I right? Or radial vector, whatever you call, with respect to second coordinate, that is along what you call second unit vector. The proportionality factor we write H2. Similarly, dou r by dou q3, we are going to write it as H3 into E3 cap. Is that okay? H3 into E3 cap. Now, what are these H1, H2, H3? Look at here. This H1, H2, H3. H1 is nothing but mod of dou r by dou q1. Okay. Or let me write like this. Hi is equal to mod of dou r by dou qi. That's the best idea. Okay. We shall save some time. And can I write similarly EI cap? EI cap. So that is 1 by Hi times dou r by dou qi. Can I write like this? 1 by Hi times dou r by dou qi. Or if you see this one carefully, this is dou r by dou qi divided by mod of dou r by dou qi. Check this out. So this EI cap, that's equal to dou r by dou qi, okay, whole divided by mod of dou r by dou qi. Check this out. Is that okay? I mean, this Hi I have just substituted, okay? So you better remember this one to define what you call your unit vector, because we start with Cartesian coordinate, we take the transformation to spherical and cylindrical coordinate system, then this expression is very relevant for us, okay? To define or to what you call find the relation between what you call unit vectors of old and new coordinate system, like that, okay? So that's very important formula. So here I have taken this expression directly, try to grab the more logic behind this one from what you call Weber. I think rest of the things will follow actually. Is that okay? Speak out. Actually this dr is nothing but our dl vector, okay? This dr, whatever we define, that's nothing but dl vector. So shall I proceed here?
Yes, sir.
Now, actually, Now look at here. Suppose if you want to define velocity, okay, dr by dt. So this is nothing but take this whole expression, divide by dt, divide by dt, divide by dt, divide by dt actually. Okay, that kind of expression we can easily write if you write that way. Okay, there we are going to apply like this to define velocity in terms of different coordinate system. Okay, in case of classical mechanics. Okay, so we shall deal with that one later. But it is not relevant for electrodynamics, okay, to define velocity in a different coordinate system. It's not much relevant here. So our idea is different here. Yes. Now again, just keep this one in mind. Whenever we define any coordinate system, along with Q1, Q2, Q3, along with E1 cap, E2 cap, E3 cap, we define H1, H2, H3, okay. I think that's called as metric element. Anyone, can you quote if you know? Let me try the tensor analysis later, okay, after the syllabus. We have to define H1, H2, H3, okay? Because most of your divergence, curl, gradient, Laplacian, this can be written using this H1, H2, H3, okay? Speak out. And this Q1, Q2, Q3, this defines dQ1, dQ2, dQ1, dQ2, dQ3, am I right? I mean, their respective differentials, okay? And this H1, H2, H3, with respect to some particular coordinate system, that's also very, very important. Is that okay? Look at here. Now let me go for Cartesian coordinate. I mean, for Cartesian coordinate, we already know all of this, okay? Wait a second. Let me define some more things here. Again, this dr vector I have defined, okay? That dr vector, again, just rewrite the dr vector after I defined this one. I didn't rewrite that one. Just can you rewrite? So that is H1 into dQ1 into E1 cap. So check your notes. Dr vector, that's equal to what I have written, dou r by dou Q1 into dQ1. Am I right? So this one is H1 into E1 cap. That's what we have written. Plus dou r by dou Q2 into dQ2, isn't it? Dou r by dou Q3 into dQ3, isn't it? Now this one, what we have written is a H2 into E2 cap, am I right? That's what we have written, this one, dQ2, plus H3 into E3 cap, dQ3. This is how we can define dr vector, okay? That's why H1, H2, H3, Q1, again, if you define Q1, Q2, Q3 as your coordinate system, and if you define H1, H2, H3, you can write your infinitesimal displacement vector in any particular coordinate system. That's why I told, again, if you are talking about some particular coordinate system, Q1, Q2, Q3, that means you should know this H1, H2, H3, respectively. What is that H1, H2, H3? Let me write Hi is equal to dou r by dou Qi divided by mod of dou r by dou Qi, I equal to 1 to 3. Just rewrite this dr vector like this. Is that okay? Now let me go for Cartesian coordinate. We shall see what would happen and all, okay? Actually, I can define my area vectors, these things, okay? Look at here. If you want to write area vector along, suppose, E1 cap, okay? Area vector can have different directions. It all depends on the surface, isn't it? That can be along E1 cap, E2 cap, E3 cap, or in any particular arbitrary direction, okay? Let me take area vector along first unit vector, okay? So that can be written as actually, so this can be written as H2, H3, dQ2, dQ3. Later we shall again, you will understand this one, okay? Suppose if you want area vector in second unit vector direction, E2 cap, you have to write H1, H3, except this H2, okay? I hope you can get the logic. dQ1, dQ3 into E2 cap. Speak out. dA3, area vector in third unit vector direction. I mean, we have taken that one, right? Area vector perpendicular to XY plane, that means along Z axis, along Y axis, like that. While doing that, surface integral over a cube, I think you have used this one, am I right? Speak out. While doing surface integral over a cube, okay, over the surface of the cube, I think you have done this one actually. Let me give the example. Suppose if you want what you call area vector, which is along z cap direction, okay? What you have taken here, I mean, you are defining this area vector. Again, this area vector is perpendicular. Again, it is along z cap, means that area, whatever you are defining, that is perpendicular to z cap. That's a plane which is perpendicular to z cap. That was a xy plane actually. So that you have written it as dx into dy, or sometimes you put minus here, depending on the what you call particular condition, isn't it? That's what I have written. So in case of Cartesian, that h1, h2 are 1 actually. Let me define that one. Is that okay? So that's what we are going to generalize in case of what you call most general situation. Okay. So dA3, that's equal to, look at here, h1, h2, dq1, dq2 into E3 cap. Area vector in a different what you call unit vector directions. Is that okay? The one of the best example is this one. We have used this one in case of our what you call integral over a cube and all. Okay, over this. So in case of, again, we dealt whatever the problem we dealt until now, that is Cartesian coordinate only. Okay. Now we need to transform to other system. That's why we better to remember like this. Am I right? So that we don't have to by heart much things here. Is that okay? So similarly, if you write what you call your volume element, okay, for a particular coordinate system, what will happen is h1, h2, h3, dq1, dq2, dq3. This is the volume element. See, actually, this is a kind of cross product. I don't exactly remember what kind of cross product it is. Okay, I think you write dr vector. Am I right? h1, dq1, e1 cap. Am I right? Plus h2 dq2 e2 cap plus h3 dq3 e3 cap. Am I right? I think this is a scalar triple product of this vector, and this vector. I hope so. This volume element. Where e1 dot e2 cross e3, that modulus will be 1. I hope so. I don't exactly remember. Just check that out, how they define volume element. But in the most general case, we are going to define like this. Since this h1, h2, h3 are 1, d tau will be equal to dx, dy, dz. 1 into 1 into 1, dx, dy, dz in case of Cartesian coordinate. Okay, that we already know. So similarly, we define gradient, divergence, and curl. Okay, suppose if you want to define gradient of a scalar, okay, that scalar should be imagined that's a function of q1, q2, q3, our what you call this coordinate system. Okay, your gradient of a scalar, that is defined like this: e1 cap divided by h1, e1 cap divided by h1, dou t by dou q1, okay, plus e2 cap by h2, dou t by dou q2, okay, plus e3 cap by h3, dou t by dou q3. So similarly, you can define divergence like this. Look at here. Let me briefly give this one. Later you can see that one in the book. Okay. Divergence of a vector field. Okay. If you have a vector field, look at here. If you have a vector field, that vector field should be imagined like this. Okay. V1 into E1 cap plus V2 into E2 cap plus V3 into E3 cap. Just like, suppose if you have a vector field, okay, VR into R cap plus V theta into theta cap plus V phi into phi cap. That's what I'm talking about here. Is that okay? In the most general case. Now, if you imagine your vector field is written in terms of respective component or component along respective unit vector direction, you can say this is the component along R cap, component of this vector along R cap, component of vector along theta cap. This is theta, this is phi. Theta, phi. Is that okay? V phi. Okay. So like that. Now you can define divergence of a vector field. Let me define everything here so that I can write down the expression. That's equal to 1 by, I think, h1, h2, h3. 1 by h1, h2, h3. Dou by dou q1, okay, V1 H2 H3, you will get a logic, okay, you will get a mnemonics. Dou by dou Q2 V2, okay, other two H, I mean H1 H3, okay, plus dou by dou Q3 plus dou by dou Q3, okay, V3 H1 H2, V3 H1 H2, V3 H1 H2. Speak out. So similarly, let me write the curl also, so that later I don't have to write this abstract thing. I can just apply this one. Okay. So curl of a vector field, again vector field should be written like this. Curl of a vector field is, I think, H1 into E1 cap, H2 into E2 cap. We have written X cap, Y cap, Z cap here because H1, H2, H3 were 1 for Cartesian coordinate. So H3 into E3 cap, okay, dou by dou Q1, dou by dou Q2, dou by dou Q3, okay, H1 into V1, H2 into V2, H3 into V3. This is curl. And Laplacian is quite lengthy actually. Let me write that one, okay, Laplacian, but it's quite lengthy. We better remember Laplacian part directly, not in this format actually. We shall see that one, okay? Because this format is lengthy for Laplacian, but this, if you remember this for gradient divergence and curl, you better remember this one. Later, again, for a respective coordinate system, find what is E1 cap, E2 cap, E3 cap, H1, H2, H3, Q1, Q2, Q3, you just substitute. Okay, that's the basic idea. Wait a second. Let me define Laplacian also. Del square of some scalar, okay? That scalar to be imagined as function of Q1, Q2, Q3, okay? So that's equal to 1 by H1, H2, H3, okay? Dou by dou Q1, okay? It's the second derivative, isn't it? Dou by dou Q1 of H2, H3 divided by H1 into dou by dou Q1 of T. That okay? Like this. It's a second derivative actually, okay? Plus dou by dou Q2, okay? H2, H1, H3, dou by dou Q2 of T. I hope you can write one more term. Is that okay? With the same logic. Speak up.
Yes, sir.
But look at here, this is quite lengthy. That's why what we prefer, what I suggest is, just like we have already taken Laplacian in case of spherical polar coordinate, in case of Schrodinger equation, you better remember directly. For Laplacian part, again this method is quite lengthy. I mean, first writing this one and then substituting H1, H2, H3, that's too lengthy. Okay, we shall see that one. Now let me go for Cartesian coordinate. Cartesian coordinate. So first thing is you have to define dr vector, okay? X cap, y cap, z cap, isn't it? If you have one radial vector, okay, or one position vector r, that position is written by x comma y comma z, okay? At this position, again, if you want to define x cap, y cap, z cap, you have to define like this only. This x cap, y cap, z cap. The main important part of Cartesian coordinate is this unit vector will not change. Whatever the spatial position you take, okay, that unit vector are fixed actually, okay. So you will see in other two coordinate system, they will vary with respect to different point, okay. Now look at here. So now what you do here, so you are going to take projection on xy plane, isn't it? So can you imagine this one? Is that okay? Kind of door I told earlier, isn't it? You have to imagine this one kind of door, this one, this whole thing. So now we are going to what you call, we again, this is z actually. This distance is z. So then we take projection here. So this is what you call x actually. So we take projection along this axis, okay, y axis, okay, like this. So this is y actually, isn't it? This distance is y, this is origin. I hope you know this one, am I right? In case of Cartesian coordinate, we write like this. Now what we do is, we define x into x cap, am I right? This vector. And then y into y cap, isn't it? Y into y cap, this vector, am I right? Plus y into y cap. What is the resultant vector? That is this one, isn't it? Figure out. X into x cap, y into y cap. The resultant is this one, isn't it? Plus this vector is added to z into z cap. Am I right? This vector. Speak out. This vector added to this vector, you get r vector. Am I right? Z into z cap. This is x into x cap plus y into y cap. It is added to z into z cap. You get r vector. Actually, you define r vector like this. Is that okay? So this is very basic definition. So from this, everything will start actually. So can I rewrite? That's equal to x into x cap plus y into y cap plus z into z cap. And if you have any other vector, you are going to write like this, okay? Ax into x cap plus ay into y cap plus az into z cap. Am I right? Whenever we define Cartesian coordinates, we write like this: x comma y comma z. Okay? So x cap comma y cap comma z cap. Okay? Now next thing is, once you define this r vector, okay, you can define dr vector. Is that okay? You better remember dr vector like this, okay? Again, once you define this r vector, better just like h1, h2, h3, define hx, hy, hz first. Is that okay? Just like h1, h2, h3. What is hx? This is dou r by dou x divided by mod of dou r by dou x. No, that is E x cap vector, am I right? Wait a second. This is x cap vector, x cap. X cap is defined like this, am I right? Wait a second. How did we define h1 or hx here? That's equal to mod of dou r by dou x. Am I right? Check this out. Similarly, hy and hz, okay? So that's why dr vector I can write as hx dx into x cap plus hy dy into y cap. We know this one already, okay? Because unit vectors will not vary. That's why this differential is equal to dx into x cap, dy into y cap, dz into z cap. Okay? When you take any minute changes here, unit vectors will not change. Okay? Only these coordinates will change. Okay? So, but in case of other two coordinate system, it's quite different. Unit vectors also changes actually. That's why it is not that straightforward. Okay? So, hz dz into z cap. Okay? So, but you can observe this one, dou r by dou x. What is dou r by dou x? Can you tell me?
1.
No, dou r vector by dou x is x cap itself. These two part is 0. Again, you can write like this. You can take x cap outside. You can write dou by dou x of x actually. Okay? Because x cap will not change, isn't it? While taking the derivative, you have one constant. That's this vector part is constant. You take the what you call derivative of this variable part. So that's why that's equal to x cap itself, okay? So that's why modulus of that one, that's equal to 1. Is that okay? So the similar thing will happen for hy and hz. That's equal to 1 and 1. Check this out. Is that okay? So that's why whenever you write Cartesian coordinate, you have to write, look at here, hx, hy, hz, okay, that is equivalent to 1, 1, 1. You got to define these things because everything can be written in terms of them, am I right? What is this one? Dx x cap plus dy y cap plus dz z cap. We already know this one, dr vector, or sometimes we call this one as dl vector. Most of the time we call that one as dl vector actually. So remember how this x cap, y cap, z cap are defined. Okay, that's equal to dou r by dou x into mod of dou r by dou x. Okay, I'm going to use this formula for other two coordinate system. Here you know how you defined. Okay, but other two coordinate system, again you start with the Cartesian, you take the transformation. That's why this definition of unit vector is also very important. Okay, and h1, h2, h3, or here I have taken In place of H1, I have taken Hx, okay? Because I have taken X, Y, Z here. There I have taken Q1, Q2, Q3. So again, respectively, I have taken Hx, Hy, Hz. I hope you are okay with it. Speak out. So this is a dl vector or dr vector, okay? Then look at here. Suppose if you want to write any, area element, okay, along x cap direction. Along x cap direction. That means you are defining area element along x cap direction means, so that area vector is along x cap direction, area vector of that infinitesimal element. That means that area is parallel to zy plane. Can you imagine that one? If you are finding area vector along x cap means you are defining area vector in zy plane actually. Again. That's why that area element actually that's equal to dy into dz. Can you just imagine? Dy dz. This is how I gave the argument while dealing with that Cartesian surface integral. But here you have to write like this. dAx should be x cap, okay? Speak out, hy, hz, okay? dy dz into x cap. You have to write like this. I did define that one directly. Do you remember? Again, if you have zy plane, okay? If you have y here, z here, your x is like this, am I right? If you want to define elementary area which is along x cap direction, that means you are defining that elementary area parallel to zy plane. And that elementary area is dy dz actually, dy into dz. So that's how it happened actually. Again, I defined this one logically, am I right? Dy dz into x cap. Now you better to write this one in terms of this one so that when you go for other two coordinate system, it will be easy for us. Speak out. Similarly, day, okay, that means area vector along y cap direction, okay, that's equal to hx, hz, dx, dz. So that's equal to dx, dz along y cap. Sometimes we take negative sign, isn't it? Whether it is along, it all depends on the situation, am I right? Sometimes we have taken along plus y cap, otherwise along minus y cap, isn't it? Depending on the a situation. Similarly, dAz vector, that's equal to hx, hy, dy, dx, dy, z cap. Is that okay? dx, dy, z cap. I think you did apply this one in case of that surface integral, etc. And the next one is d tau. How did I define d tau? h1, h2, h3, dq1, dq2, dq3. That's why it's equal to hx, hy, hz, dx, dy, dz. So that's equal to dx, dy, dz itself. Am I right? Volume element in case of Cartesian coordinate. Now we already know what are these gradient, divergence and curl. Okay. Gradient of t, if t is imagined as a function of x, y, z, okay. What is gradient of t? That's equal to what I have written? X cap divided by hx, like that, dou by dou x of t, plus y cap divided by hy, dou by dou y of t, plus z cap divided by hz, dou by dou z of t, isn't it? So since hx, hy, hz are 1, you can write x cap into dou t by dou x, okay, plus y cap into dou t by dou y, plus z cap into dou t by dou z. This is how you have written. Speak out. Like the divergence and curl, since h1, h2, h3 are 1, I hope you can write that one. We again, whatever we have discussed earlier, so those are with respect to Cartesian coordinate. Now we shall take transformation to other two coordinates. You can write other part, isn't it? But our earlier formula should be seen like this so that we can, if you go for other coordinate system, it will be very easy for us, okay? So this was earlier gradient formula, but it should be seen like this. And in the most general case, I think we can even derive this one. So Q1, Q2, Q3, E1 cap, E2 cap, E3 cap, like that, whatever I have written earlier. Is that okay? Speak out. Now let me take the transformation to spherical polar coordinate, okay? Okay, here our coordinates are x, y, z, am I right? Sorry, r, theta, phi, am I right? Our coordinates. R is, we call it as radial distance, or that's a scalar distance from the origin, distance of a point in space from the origin. So theta and phi we can define, isn't it? So where r will goes from 0 to infinity, isn't it? Theta will goes from anyone 0 to pi. This phi will goes from 0 to 2 pi. Can you find the difference between theta and phi? My handwriting. Speak out.
Yes.
Usually what we do, we start with the Cartesian coordinate, then we take the transformation, okay? We call that as transformation equation. We shall see that one in case of classical mechanics. We use the transformation equation actually. So now let me take what you call Cartesian coordinate. Let me start with Cartesian coordinate, x cap, y cap and z cap. Is that okay? So this is my what you call position vector of a point in space. Now that point in space is can be written by x comma y comma z, or that can be specified by r comma theta comma phi. Okay, this is my position vector, r vector. This r is nothing but what you call magnitude of this position vector. You know that one, isn't it? This is a point in space. Now what you do? Again, you take projection on xy plane. So, and you are going to draw it like this, isn't it? Speak out. And then I did imagine a kind of door kind of thing. Again, that's very important. Okay, that imagination is very important here. So like this, am I right? Okay, are you okay with this one? This is perpendicular, whatever drawn to from this point to z axis. Can you imagine that one? 3 dimension? Speak out. So you can imagine this is a kind of door actually, a kind of door. Can you imagine? Speak out. Now look at here. This is defined as, again, this distance itself is r, okay? You know that one. This is theta. So this is phi actually. Okay? So now to relate x comma x, y, z to r theta phi, you have to do like this actually. If you do it like this, this is your x, am I right? This distance is x. That x is nothing but, okay, let me try to write. If this is r, okay, if this is r, if this is theta, what is this one? Speak out. R sine theta. Imagine this is a plane. So these two are what you call, these two are perpendicular to each other, am I right? So can you just imagine that one?
Yes, sir.
Yeah. So then this is r sine theta, this is r cos theta. This z coordinate is itself r cos theta actually. R cos theta. You can write z equal to r cos theta. Okay. This is r sine theta. If you take x projection, okay, you will get r sine theta into cos phi. R sine theta into cos phi. Is that okay? If you take y projection, okay, like this. So this is y coordinate. Am I right? This whole thing is y coordinate of this point. That y is equal to r sine theta. Okay, that is this one. Again, this is a orthogonal resolution actually. Okay, r sine theta into sine phi. That's how we define x equal to r sine theta cos phi, y is equal to r sine theta sine phi, z is equal to r cos theta. It is x, y, z in terms of r theta phi. And similarly, you can invert this equation. R is equal to root of x square plus y square plus z square. We already know. Okay. So theta is equal to, how do you define theta here?
The root of x square plus y square.
Better to define theta here. Cos theta. Am I right? Cos inverse of z by r. R is nothing but root of x square plus y square plus z square. Z divided by r actually. Okay. I mean, I need a old coordinate in terms of new coordinate. Yeah, speak out. New coordinate in. Speak out. No. Pi can be written as tan inverse of y by x. This pi, okay. This is y. This is x. You can define it as, should be defined using this one. Z is equal to r cos theta. Am I right? That's why theta is equal to cos inverse of z by r. That's how I have written. This is new coordinate variables in terms of old one. I mean, we don't use that one much. Is that okay? Now, the first thing that we need to define, that is r. That's equal to x into x cap, y into y cap, z into z cap. But we know what is x, y, z here. Okay. So that's why x is r sin theta cos phi. Okay. X cap plus r sin theta sin phi.
Yes, sir.
Now we define, look at here, dr vector. What is dr vector? Dou r by dou r into dr, one of the coordinates, plus dou r by dou theta into d theta, plus dou r by dou phi into d phi. So that can be written as, I think this one we have written as hr, am I right? hr dr into hr into r cap, unit vector along r cap, isn't it? Speak out. That's how we have written dou r by dou r, am I right? Now we define like this. Dou r by dou r is equal to hr into er cap. Er cap, let me write it later. Dr into er cap plus h theta d theta into theta cap plus h phi d phi into phi cap. You can't write like this. Okay, r vector, you can't write r into r cap plus theta into theta cap plus phi into phi cap. This would be wrong. Okay, this is again, these are wrong. Are you getting my point? You have to define it like this actually, and then you have to try to define in terms of a new system. We shall try this one. Okay, these things are wrong. Okay, speak out. They don't even dimensionally match actually. Okay. Now define HR. What is HR? Is equal to mod of dou r by dou r. Am I right? From this equation, look at here. Why I have taken this equation? Because in this equation, it's very easy to take vector derivative because unit vectors are not variable. We shall see later. Let me define what you call your what you call unit vector r cap, theta cap, phi cap. Okay. R cap, theta cap, phi cap. Okay. So these are variable. I mean, those are different for different point in space. But these are not variable. That's why it is very easy to take the derivative. Am I right? Because if you take dou r by dou r, what will happen is this will go, this will be 1, this will be 1, this will be 1, x cap, y cap, z cap. If you take a mod, can you imagine? Can you just do this one? This is equal to actually mod of, okay, sin theta cos phi x cap plus sin theta sin phi y cap plus cos theta z cap actually, after taking derivative with respect to r. If you take a mod of this one, you have to take root of square and adding. Okay, that will be 1 actually. You just check that out. From trigonometry, you can take some sin square theta outside. Okay, and then something will happen. Just what you call. So check that out. This will be equal to 1 hr. H theta, h phi yourself. Okay. So h theta, that's equal to mod of dou r by dou theta. Take derivative with respect to theta. Keep everything else same. Okay. Sin theta will become cos theta. Cos theta here. This is minus sin theta. Okay. When you take the mod, I think you will get r. Check that out. Do it yourself. Okay. So when you find h phi, look at here. That's equal to mod of dou r by dou phi. Okay, using this one again. So that is actually r sin theta. Do this. So that's why whenever I define spherical polar coordinates, soon after I better to define dr, what you call hr, h theta, h phi, so that I can define these things very quickly, isn't it? Speak out. So shall I rub it out? let me write it here, HR, H theta, H phi. That is equal to 1 R sin theta. You better remember like this. 1 R sin theta. And in that format, you can write your dr, or sometimes we write it as dl vector. Am I right? dl vector, that's equal to HR equal to 1 dr r cap. Actually, I have written er cap. You can write as r cap itself. Okay. dr r cap plus h theta is r. Okay. R d theta theta cap. Look at the dimensions now. Is that okay? Length like that. Okay. Plus R sin theta H phi. Okay. Into d phi. D phi cap. This is your infinitesimal displacement vector. Is that okay? Speak out. Now, if you want to define, look at here, r cap, theta cap, phi cap in terms of x, y, z. Okay, let me give it as a homework. Okay, that he has given, express r cap, theta cap, pi cap in terms of x cap, y cap, z cap. Okay, so if you want to define r cap, okay, r cap should be defined as dou r by dou r whole divided by mod of dou r by dou r. You know this one, mod of dou r by dou r, you know that one, that is 1 by hr, isn't it? 1 by hr times dou r by dou r. Okay. Now you can write r cap in terms of x cap, y cap, z cap. Similarly, you can write theta cap in terms of x cap, y cap, z cap. These equations are required somewhere. Okay. These new unit vector in terms of old unit vector. These relations are somewhere required. Okay. In some problem, do that one. He has given that one as a problem actually. Okay. Dou r by dou theta divided by mod of dou r by dou theta. Okay. Is equal to 1 by h theta dou r by dou theta. Similarly, phi cap is equal to 1 by h phi, okay, dou r by dou phi, okay. Thereby, write new unit vector in terms of old unit vector using this expression, whatever I have written. Do this also. Is that okay? Because somewhere that is required for the problem. Over. We shall see what are these unit vector, how to represent these unit vectors in space and all. Okay, we shall see that one in a moment. But after this infinitesimal displacement vector, what I defined is I defined area vectors. Am I right? dA vector, okay, along r cap. Suppose I'll write dAr. How to write that one? Speak out. H theta, H phi, d theta, d phi into r cap. Now again write down this one. What is h theta into h phi? That is r square sin theta. Okay, d theta, d phi actually. You can get even logic of this one also. Okay, look at here. Again, you should have a idea about your what you call. I think in scattering theory we have taken solid angle idea. Take a sphere of constant what you call distance again. I mean with some radius. Okay. Then how do you define what you call area vector along r cap direction? I hope you know r cap direction means suppose if you have a what you call area vector here, patch of area here. Okay. R cap is what you call radially outward. Am I right? I hope you can imagine what is the r cap direction. This is r cap direction actually. If this is r vector, this is r cap direction. Okay. I hope you can grab the r cap direction. Is that okay? If you have patch of area, your r cap is perpendicular to the surface, isn't it? You can define like this r cap. Can you imagine that one?
Sir?
So this is actually r vector from origin to point on the surface of the sphere, r vector. R cap is what you call outward from the what you call origin. You can just define that one. No, again, there are different ways of defining theta. How do you define tan theta here? From tan theta, that's equal to this by this, am I right? This is r sin theta divided by r cos theta. I mean, there are different ways of defining that one. Again, you are talking about earlier one, am I right? Transformation equation. Just work it out again, okay? Now look at here. What I'm saying here is, look at here. So this patch will form a kind of solid angle with respect to origin actually. Can you just, this patch on the surface of the sphere, okay? So take it as a sphere, okay? So take it as a sphere. That patch will form a kind of solid angle. I hope the sine theta d theta d phi is that solid angle. And solid angle multiplied with what you call r square, somehow that gave you this area, okay? I mean, do you remember I defined what you call area element in case of plane polar coordinate for some problem? What was this one? If this is d theta, okay? If this is dr, am I right? So this is theta, r dr d theta actually, area element in case of plane polar coordinate. So similar things will follow, but it's a three-dimensional thing actually. In case of this area element, okay? We call this a solid angle, sine theta d theta d phi. I hope you remember. Okay, try to link that one with some what you call physical part, because here I'm writing it as a formula, isn't it? Is it okay? This is the most used area vector actually, okay? Most used area vector, elementary area vector along r cap direction, r square sine theta d phi r into r cap.
Sir, we can get it, sir.
Like this only? Like this idea only?
Yes, sir, by projecting this on this plane, xy plane, this area, on xy plane, we have d5. And then using parallel.
Like this you are saying, this projection? Like this?
Yes, sir.
Patch like this? Yeah.
Yes, sir. Yes, sir.
Yeah, anyway, but again, if you, for application part, even if you remember, you can apply that, okay? Similarly, you can define dA theta. Now, so one of you quickly tell me, what is this one? It is along theta cap. What is this one? Speak out.
HR,
HR,
H5,
H phi, dr d phi into theta cap. Into theta cap, isn't it? Speak out. So similarly, dA phi, that's equal to along phi cap direction, HR H theta, dr d theta, that's it. But these are not much used, but you have to do some problem related, again, where these are also used, okay? I mean, you will get a full idea about that, okay? Theta is equal to arc tan root of x square plus y square plus z square. Can I define z is equal to r cos theta? Am I right? Is this correct? Then cos theta is equal to r by z by r. So theta is equal to cos inverse of z by r is root of x square plus y square plus z square. You can write in different way also, okay? I think whatever you are saying, that also may be correct.
X square plus y square equal to r square sin square theta over.
So it's okay. You can write the same thing in terms of tan theta. You can define tan theta and then you can define tan inverse, isn't it? What is tan theta? R sin theta divided by r cos theta.
No, sir, it is like x under the root of x square plus y square. This way. Sir, not in sir r, but x square plus y square.
That will again, if I define tan theta, again, how do you?
Sir, here r equal to root of x square plus y square plus.
No, am I right in this expression or not? So again, you may try to write in different way. Yeah, just write in your way. That's correct. Okay. Just work out the trigonometry properly. That's it. Okay. Yeah, leave it. Come to this point. And similarly, you can write your volume element in case of spherical polar coordinate HR, H theta, H phi, dr, d theta, d phi. Okay. That's equal to r square sin theta dr d theta d phi. This is also very frequently used. If you want to do the integral in case of spherical polar coordinate, you may need to use that one. Shall I move on? This dA vector, d tau vector, this dl vector, these are required to do integrals. Okay, volume integral, surface integral, line integral, like that. Now, these are the derivatives, am I right? If you have what you call some scalar field, which can be written in terms of r theta phi, am I right? Then gradient of that scalar field can be written like this. How we have written? E1 cap divided by H1, isn't it like that? E1 cap divided by H1.
1 by
So here r cap divided by HR, can I write like this? Dou by dou r of t. This is 1 actually. Plus theta cap divided by H theta. Dou by dou theta of t. Plus phi cap divided by H phi. Dou by dou phi of t again. Now rewrite that one, okay? So that's equal to r cap into dou t by dou r plus theta cap divided by r, am I right? Or 1 by r, dou by dou theta of t plus phi cap divided by r sin theta, dou by dou phi of t. Is that okay? I hope you can deal with this one. Speak up. Let me rub out this one for a time. I'll draw it again. So similarly, you can define suppose if you have a vector field, okay, you can write it like this: V r r cap plus V theta theta cap plus V phi phi cap. Okay. Now you can write the divergence of that vector field. Divergence of the vector field like 1 by HR, H theta, H phi. Okay. What I have written expression? Anyone? Speak out. Dou by dou r, V r, other two. H theta, H phi. Yeah. H to H3 like that. Okay. Dou by dou theta, V theta, H r, H phi. Dou by dou phi. Yeah, speak out. V phi. H theta. Now substitute and rearrange, okay? Can you do that one? I'll save some time. Substitute and rearrange them. I think some part may come common, okay? Because whenever you take derivative, suppose if you get sin theta here, am I right? H phi is sin theta will come. That sin theta will come outside. That will cancel with sin theta, whatever comes here, okay? Simplify this one. Again, you have to write V in terms of VR, V theta, V phi. Then only this formula is valid. You have to substitute those VR, V theta, V phi. Okay. So similarly, curl of a vector field. Curl of a vector field. That's equal to, okay, HR r cap, H theta theta cap, H phi phi cap, dou by dou r, dou by dou theta, dou by dou phi. Okay. Again, HR VR, H theta V theta, H phi V phi. Check this out. And you can write like this. Am I right? R cap, R theta cap, R sin theta, phi cap like this. Dou by dou R, dou by dou theta, dou by dou phi. Check this out like that. I hope you can substitute those. Is that okay? But Laplacian is too lengthy. That's what I think I have written. Laplacian. Isn't it? Laplacian of a scalar fields to be imagined as a function of r theta phi. Okay. Now this Laplacian is quite lengthy actually. Okay. So that's why I suggest you to remember Laplacian directly, not from in terms of this one and then converting. Okay. That's equal to 1 by r square dou by dou r square dou t by dou r. Am I right? Check this out. Plus 1 by r square sin theta dou by dou theta sin theta dou t by dou theta. Am I right? Anyone? Check this out. Plus 1 by r square sin square theta dou square t by rho phi square. Now you better remember this one, because writing in this format and then converting is too time consuming. That's what I felt. Okay, and that's your choice again. If you forgot, I think you can do like that. Is that okay? Now we shall go back to what are these unit vectors. Okay, this is very important part. Z cap, okay, R, is that okay? Speak out. If this is R vector, again, if you take a point here, that R cap direction is this one. R cap direction. Can you see this chalk piece color? R cap direction is this one. And that R cap vector is on this plane. This plane, can you imagine this plane? Wait a second, let me take some color chalk piece. Let me imagine this is a plane, okay? This is one plane, okay? So these two are perpendicular direction. You can just imagine this one, isn't it? Kind of door, you can just like that. R cap is in this direction. Am I right? Now look at here. So theta cap, again, these are orthogonal coordinate system. R cap, theta cap are perpendicular to each other. But while defining theta cap, you should be quite careful, okay? If you write R cap like this, okay? If you write R cap like this, so your theta cap can be written like this actually, okay? So that is perpendicular to R cap, obviously, no doubt, okay? This is theta cap. But theta cap is perpendicular to R cap. If you have one direction, okay, you have infinitely many perpendicular directions, isn't it? Speak out. If you just rotate again, in every time, that theta cap is perpendicular to R cap, isn't it? Speak out. For any direction, there are infinitely many, what you call, perpendicular directions. Now, what is the theta cap direction among those infinitely many directions? Now look at here, this R cap and theta cap should be on this plane, whatever I have drawn here. Is that okay? R cap, look at here, or you can deal like this. This R cap and Z cap will form a plane. That is this plane, whatever I have drawn, okay? This R cap and Z cap will form a plane, okay? Theta cap should be in the same plane. Speak out. Are you grabbing my idea? Perpendicular, yeah, that's true. But which perpendicular direction? That's very important. And you will get phi cap direction by just taking R cap cross theta cap. Okay, theta cap cross R. So phi cap. R cap, theta cap, phi cap. Am I right? R cap cross theta cap. That's equal to phi cap. Theta cap. So theta cap plus cross phi cap. That's equal to R cap. So like that you can define. So that's why once you define R cap and theta cap, phi cap is just a cross product. Am I right? R cap dot theta cap. That will be some other direction. Is that okay? You can just take it like this. Now this phi cap is perpendicular to this plane, whatever I have drawn. Can you grab this imagination? Some humming sound is coming in between. Wait a second. Now, to get a feel of this one, okay, you have to take different, look at here, if you move this point, R cap will change, theta cap will change, phi cap will change. That is the difference between Cartesian and what you call polar coordinate, okay. In case of polar coordinate, R cap, theta cap, phi cap are not fixed. They depend on the point in space. Is that okay? Now, shall we take different point in space, okay? Shall we take different point in space? Suppose let me take a point on Z axis, okay? Let me take a point on Z axis. Then my radial distance is this one, okay? This is my R vector. Then R cap is like this, okay? This is Z cap. This is my R cap. Can I draw it like this? This is my R cap. How do you define theta cap? It's quite difficult, okay, to define theta cap. Wait a second. There is one more logic to define theta. This theta is measured like this. Am I right? Speak out. Since this theta is measured like this, theta cap like this. You can also imagine like that. Since pi cap is defined like this, am I right? Pi cap, pi is defined like this. Am I right? That's why pi is perpendicular to this plane. Is that okay? Theta is defined like this. Am I right? That's why theta is perpendicular to this line in the same plane. Pi is perpendicular to the plane, isn't it? This pi is defined, again, this pi is an angle which is measured perpendicular to the plane, am I right? So that's why again you can define like that also. Actually, you can think like that also. So suppose if you take a point on z axis, if you take r cap like this, r cap is like this, okay? Your theta cap would be like this actually. Actually, if r cap is like this, okay, theta cap is like this, okay, this is x cap, y cap, z cap. The direction that is along minus x cap. Check this out, phi cap direction. Wait a second, I got small confusion. R cap, I need theta cap when theta equal to 0. Yeah, that's along phi equal to, again, it's very difficult to define theta and phi. Theta equal to 0, I can say. At this point, what is theta cap direction? How do you define theta cap direction? Quite difficult. But if you just move away from that one, you can define theta cap like this. No. Anyway, you just work out this relation, okay? R cap in terms of x cap, y cap, z cap, okay? Then substitute what is theta and phi value. That's the best idea.
Yeah, theta tends to 0 and phi tends to 0. Where the
No. You better work out this one. R cap in terms of x cap, y cap, z cap. Then put theta and phi value. Then I think you will get that one. Now, if I move that one, there will be no ambiguity, okay? But here, I feel there is some small difference, okay? Again, this R cap is like this, okay? Now, R cap, when I told R cap and Z cap will form a plane, theta cap is in the same plane. Now, R cap and Z cap are along the same direction. You don't have a plane actually, okay?
Then you can do it by rotating axis by theta angle.
Actually, whatever he has taken, I think it is going to be like this actually. Theta cap will be like this. And R cap cross theta cap, phi cap would be like this. I hope so. Let me check that out later. Or you just work it out. Phi cap will be like this, okay? Yeah, I think this is the right one. I mean, according to this relation, R cap in terms of this one actually, okay? But only here, yeah, again, I found small difficult. It's quite difficult because I told theta cap is in the plane of R cap and Z cap, okay? So now, if you take any other situation, if it is not coinciding, R cap is not coinciding with Z cap, you can define a plane containing Z cap and R cap. It is very easy. Is that okay? Suppose if you have your R vector like this, okay? So then you define your theta like this, am I right? So this is your R cap. Leave it. This is your R cap, isn't it? I mean, now you define theta cap like, again, you are going to define what you call a plane containing this R cap and Z cap. And in that plane, you are going to define theta cap actually. And phi cap would be what you call given by the cross product, R cap cross theta cap. Look at here. R cap cross theta cap. Here R cap cross theta cap. R cap cross theta cap. It will be like this actually. So can you imagine? Now you have to define a what you call plane. This plane, and this theta cap and R cap are on this plane actually. That's how you have to imagine. Can you grab this idea? Now wait a second. We shall try to experience much more. Then I think we may be able to grab complete idea. Again, let me take a Cartesian coordinate x cap, y cap, z cap. Okay. Can you just write theta cap is along x cap actually, r cap is along z cap. If r cap is along z cap, theta cap is along x cap, It's a cross product, am I right? Phi cap is along y cap only, okay? Check that out. Now let me take a point on y-axis, okay? Because it's quite easy to compare, that's it, okay? Point on y-axis, let me write r. Then obviously r cap is along y cap, am I right? R cap vector like this. Now I told define r cap and z cap plane, that is zy plane itself, and your theta cap is like this. Is that okay? Now r cap cross, again obviously now you can write r cap is along what you call y cap, theta cap is along minus z cap, isn't it? Can you just imagine this is a plane, am I right? Theta cap is along minus z cap here. I'm just comparing, okay? So now phi cap, which is a cross product of r cap cross theta cap, you can just imagine like this, or r cap cross theta cap, that's equal to minus x cap actually, am I right? Check this out. Y cap cross z, it is here. I have to draw it like this in the three-dimensional picture, that is phi cap direction. On y-axis, you will have r cap, theta cap, phi cap like this. Is that okay? Let me take on x-axis, what would happen? Okay, on x-axis, suppose I have to take a point here. So this is my r vector, okay? So this is my r cap. Now actually you can imagine how you, this is the theta value, right? Theta equal to 90 degrees. This is how you define theta. So if you define r cap, if I have to define theta cap, like how, again, like in the direction how you measure this theta, that's how I feel comfortable, okay? Like that again, here you measure theta like this, am I right? Like that again, your theta cap is like this. If this is r cap, okay? So this is theta cap. Again, that is minus z cap direction, okay? Then r cap cross theta cap. R cap cross theta cap, am I right? Y cap direction. This is the phi cap direction. Is that okay? Like that. So take a point on negative z axis, okay? Take a point on negative z axis and try to find what is r cap, theta cap, phi cap direction, because these ideas are required somewhere in the problem later, okay? So do that one, or if you do the problem, I think. So actually we write it as rho phi z, okay? Rho phi z, but rho is the symbol that is used for charge density also, okay? So that's why what we do is we are going to use S phi z, okay? In place of rho, we use S. Again, what we do is we start with the Cartesian coordinate, okay? Then we take the transformation as earlier, okay? We start with the Cartesian coordinate, we take the transformation. That's how we deal with that one, okay? So, Cartesian coordinate again. X, Y and Z. What is disturbing quite? X, Y, Z. X cap, Y cap, Z cap, you can think like that, okay? Again, let me take a position vector in space, okay? You have to work out this one, okay? Because I worked out spherical polar coordinate. Again, using the same idea, just to generalize that one to what you call this coordinate system. This is R vector, okay? Again, let me take a projection. Okay, can you imagine a plane like this? This plane. Now, again, this Z coordinate is Z itself, okay? This Z distance itself, okay? Phi is whatever the phi we defined earlier, phi is itself, okay? The same phi. But S is perpendicular distance from the Z. This is S, perpendicular distance from the Z. This point can be written in terms of S phi Z. This point can be represented in terms of that one. Again, S is 0 to infinity. S cannot be negative. Phi is 0 to 2 phi. But Z is minus infinity to plus infinity. Z is, this is positive Z, negative Z. It is minus infinity to plus infinity. Now again, take the transformation equation. Again, how do you define X? Quickly, if this is yes, obviously this is yes. Can you just imagine? Speak out. This is also yes. So this is yes cos phi. X is equal to yes cos phi. So this is y, am I right? This y is equal to s sine phi. Check this out. Z equal to z itself. Okay. So can I write like this? X is equal to s cos phi. Y is equal to s sine phi. Z is equal to z itself. If you want to invert this one, how do you write s? S is equal to root of x square plus y square. Isn't it? If you square and add. And phi is equal to tan inverse of y by x. Okay. Z is equal to z. These are the transformation equations. And again you can write r vector in terms of s cos phi x cap plus s sin phi y cap plus z into z cap. Z part remains same. Very similar to Cartesian coordinate. Is that okay? Now start defining dr. Okay, start defining hs, h phi, hz. Is that okay? So again, once you write these things, you have to define hs, h phi, hz also. S cap, phi cap, z cap. These are the unit vectors. Okay, hs, h phi, hz. Okay, these are actually 1 s 1. Okay, 1 s 1. I think this s is sometimes called as axial distance. We take it as an axis. It's an axial distance. Just like we call this as a radial distance. Am I right? R. S is called as axial distance in many cases. Okay. Pi is azimuthal angle. Z is z itself. Okay. Can you define the further thing? Is that okay? Speak out. Just like dr, how do you write dr? I think hs ds s cap plus h phi d phi phi cap. Am I right? Speak out. Plus hz dz z cap. Hz is 1 itself. Okay. So that's equal to ds s cap plus I think h phi is s d phi phi cap plus dz z cap. Is your dr vector or dl vector. Okay. Similarly, area vector. The most used area vector. I should not say most used because again there are different problems actually. Okay. So, but still, dA along what you call s cap direction. This is the most used one. Other two are also quite frequent. Okay. Can you quickly tell me what is this one? H. Speak out. H phi d phi dz. Am I right? S d phi dz. You can just imagine this one also. Okay. You can just find a what you call cylinder with this as a radius. Okay. You can take a what you call that surface of the cylinder. You can take a patch of the what you call patch of that one, and you can define some phi angle that is made with that one. Okay, d phi. And I think this is your dA along s cap actually. This is s cap actually. Let me define that one. Okay, this is s cap. If s is measured like this is s cap direction. Okay, like that. If s is measured like this is s cap direction. Okay. Yeah, try to do the problem. I think that will give you more idea. Okay, DAS, and that will contain dz. That will contain s d phi. This is s d phi. That is one of these I think, and then dz. That's how you get this area. Okay, try to grab the logical idea how this becomes a area element. Okay. So similarly, dAz and dA phi. Define these two. I think these are also required somewhere. Okay. dA phi. Phi cap. Z cap. How do you write? HS. H phi. DS. D phi. HS. HZ. DS. DZ. You can define like this. Like this. Suppose if you have a cylinder like this, okay, You can just imagine you define some patch of area here along Z cap, okay? Pi cap is quite difficult to imagine. You have to take one cross section, then you have to define pi cap actually. If you define A, again, whatever this red line, whatever I have drawn, okay? I mean this plane, whatever I have taken, okay? If you define a patch of area in this plane, okay? If you just define a patch of area in this plane, now that area vector will be perpendicular to that plane, that is pi cap direction actually. Like that, try to get some logical idea behind this. And then D2 volume element is equal to Hs, H phi, Hz, ds, d phi, dz. That's equal to S ds, d phi, dz. Check this out. That's your volume element, okay? So like that, can you do rest of all whatever we did for Cartesian coordinate, okay? Writing curl, divergence, gradient in terms of that one. Laplacian you better remember directly, okay? And do that one, okay? Don't, don't skip that part, because if you do that one, you may remember. Again, most of the case, you don't have to by heart. You have to, use that one frequently so that you will automatically remember. Is that okay? So similarly, write this S cap, pi cap, Z cap. Okay, how do you write S cap? Dou R by dou S divided by mod of dou R by dou S. Am I right? Using this one and all, write that in new unit vector in terms of old unit vector in terms of X cap, Y cap, Z cap. That is also required in some problem. Okay. So do everything. Let me give the homework. Yeah, we shall close this session. We shall see in the morning, because you need to solve some problems here today itself, so that tomorrow I can go to electrostatic chapter. Okay. The problems are this 1.38, 1.40, 1.39, 1.42 and 1.43. Very, very important problem that will give you a whole idea of these things, whatever I have explained here. Okay. It will give a kind of hold on this coordinate idea. You will never be scared of dealing with that one. Okay. So do this problem today only. Okay. So that tomorrow, because I'm going to cover the later part, you may end up with much more homework. Okay. And revise the Dirac delta part. Okay. Yeah, I think I will first do this Dirac delta tomorrow. Then I will move on to electrostatic. That's the best idea. So shall I upload that homework together on this fundamental theorems along with this coordinate system? Okay. Yeah, I'll do it now. Again, we shall start morning class around 6 or 6 not 5 or something, okay, in the morning, so that again we can have 2 hours comfortably. Yeah, speak up.
Sir, similar to spherical and cylindrical coordinates, how many of these coordinates we can define?
No, many coordinate system we can define, but in this this electrodynamics we are applying only these 3. Okay. But I think if you take different problem, I hope in case of some general theory of relativity, or in case of some other problem that comes in classical mechanics, we define some more coordinate system. So I heard in classical mechanics, there was one coordinate which is defined like, I think, a kind of parabolic coordinate system, which is to avoid one variable actually. We make the transformation so that we can avoid some variable. We use this coordinate system so that our problems are simple in this coordinate system. Okay. I mean, if we have a cylindrical symmetry in the problem, we go for cylindrical coordinate. If we have a spherical symmetry, we go for spherical polar coordinate. Okay. Like that, other coordinate systems can also be defined, just like I told, some parabolic coordinate system. That's what we, as I remember, in case of, wait a second.
There what 11 such systems can be defined in Weber book.
Only 11?
Each of them, they should have some common property, only then they are they should be used. Some common property is there.
Now I'm quite, I mean, okay, that's okay. I mean, why he mentioned specifically 11, am I right? Is there any theorem, mathematical theorem that we can define only 11 like that? It's quite disturbing, isn't it?
I don't remember if I read somewhere in Weber book.
Sir, I think it is for orthogonal termination.
For orthogonal, we can define only 11. That's what. But still, again, I don't know. What are the mathematical proof for that one, okay? But these three are the most used. But again, we use the coordinate system to make mathematics simple, okay? We use different coordinate system to make the mathematics simple. We shall see that one. One type of problem, if we start with Cartesian coordinate, we end up with trouble. We can't solve something, some integral and all, okay? So then we transform to what you call polar coordinate, and we did that one earlier also, in case of quantum mechanics and all, okay? So again, coordinate systems are chosen for convenience, okay? And I think, let me check that out again. In case of orthogonal only 11, is there any mathematical theorem like that? Let me check that out, okay? So that's a good question.
Sir,
Yes.
can you explain the range of theta from 0 to pi? How?
In spherical everything, take it as a door, okay? So take this door on zx plane, then pi equal to 0. Okay. Okay. Wait a second. How you should grab the what you call ranges, am I right? Ranges of this coordinate system. You should grab it like this, okay? Now, suppose if this is r vector, this is theta, okay? Now, if you vary theta, okay? If you just sweep this r vector from theta equal to 0 to theta equal to pi, what you will generate? You will generate this one, am I right? Because theta equal to 0, suppose if it sweeps again until what you call theta equal to pi. So can I take like this? So let me take a kind of what you call like this actually. Can you imagine this one?
But similarly, you can go other side also.
Wait. One second. Wait a second. What I'm saying is how these ranges sweep entire space. Okay. R runs from 0 to infinity. Let me take it later. Okay. R runs from 0 to infinity. First, let me take theta runs from 0 to pi. Then it will make this kind of what you call half of the disk. Now, if you vary your phi from 0 to 2 pi, you will get a sphere. And then if you vary r from 0 to infinity, you are spanning the entire space. Okay. So that is the basic idea. That's a very good question. I don't find theta. If you have a line, okay, so keep r constant. You just sweep that one from theta is equal to 0 to pi. You will have a half part of the disk. Okay. Then take that disk. Okay. Vary phi from 0 to 2 pi. You will have a sphere. And now vary the radius of the sphere from 0 to infinity, you will span an entire space. The same thing you do for what you call cylindrical coordinate also. Is that okay? How you span entire space using these ranges, okay? That's a very good question. Yes. Yeah, yes, speak out.
They are saying that there is an equation del square psi plus k square chi equal to 0. Only in those 11 cases, this equation is separable.
Okay, Helmholtz equation. Okay. I mean, these equations are separable only in 11 cases. We can solve the equation, partial differential equation, in only 11 cases. No, I don't know what are the other part of the applications. Okay, I mean, where it is used and all. Okay, I mean, other type of coordinate system, how to define and all. I think other coordinate systems are very difficult to imagine. Okay, so these are we take a sphere and we can imagine this. We take a cylinder and we can imagine these two systems. I don't think other coordinate systems are that easy to imagine and all. to define unit vector and all. Okay.